Hey there hackers! I'm here with another AOC solution video for day 14. This puzzle was such a tricky surprise because we got a very cryptic task in part 2 to find an image of a Christmas tree in a buzzing array of white noise. Usually the AOC problems are pretty well defined, so this is a rather special occasion to be left with so few clues to what to do. But let's see how we can tackle it with Uiua. First, let's review the puzzle. The inputs are this time not so nicely shaped, but at least each row has exactly 4 numbers in it, and some of them are negative. Each row represents a robot with its starting position and its velocity provided in the input. So we can think of a robot as a vector. In the first part, we need to perform a simulation to move all the robots at once at 100 times and figure out where they end up. Granted, when they move off the edge, they teleport to the other side and keep their direction. We also get the recipe for the safety factor, a special scoring method which divides the room in 4 quadrants and multiplies the number of robots found in each of them. Here we have the sample inputs copied to the Viva pad. Rather than splitting up the rows, we will try to get all the numbers at once. First, we create a range of 10 and convert it to text by adding the 0 character. We cannot forget about the negative numbers, so I joined the minus character too. Now we make a binary mask using the member of function, so the groups of numeric digits are highlighted in the input. We can use partition to parse all the numbers. After a little reshape, the data is nicely organized in 4 columns. Now we do have a choice here, how to arrange the inputs, and I think it's a conceptually important one. Either we leave the array like this, where each row represents all the attributes of a robot, the coordinates x and y, and the direction dx and dy. This has more of an object-oriented feel. What we'll do instead is reorganize this data, keeping in mind how we will want to use them in computations. I find this a rather more array-oriented approach. Relying on arrays, we can take advantage of pervasive operators, and some functions will perform much better when applied on a large array than applying separately on each row or element. Basically, with every step of the simulation, we want to add the second pair of numbers to the first pairs to get the new position of the robots. So we will transpose the array and split the 4 rows in half using fork, take, drop 2. Now the last value on the stack is the positions. We assign it to the name P and we assign the velocities to V. We will also save the field size as it was indicated in the task. It is different for the test and the real data. So we will need to switch later. We can also display these in the output along with some labels. This can help remembering the shapes and some of the values we need to see to compare with the puzzle examples. Calculating where the robots will be 1 second later is as simple as adding the velocities to the positions. Array languages are really good at this. Viva automatically pairs up each value in both arrays because their structure is matching. All robots can be moved at the same time with a single operation. We can observe that some values are already overflowing after just one iteration. There are negative numbers and 2 large numbers as well. These robots should teleport to the other edge of the map, which in mathematical terms means we have to take their modulus by the map size. This keeps each value in the expected range. Here it is really advantageous that we transpose the data, because both rows of the position arrays are paired with the corresponding 2 values of the field size, and the modulus is applied to every single value in each row. In some way, it's already mind-blowing that you can do this so easily in array languages like Viva. And the simple way to do as many iterations as required is multiply the velocity by the number of seconds. It's enough to use modulus once at the end. 0 is the initial position, and in part 1 we have to calculate 100 iterations. I call this the sim function, leaving the number of iterations a dynamic parameter. To visualize these coordinates in a 2D space, we can transpose the array to get each pair of x and y in a separate row, and then do an unvar. The var function is very often an essential tool in these AOC challenges. Basically, it is the gateway between the world of 2D maps and the world of coordinates. Sometimes it is more convenient to solve a problem in a 2D arrangement. The one caveat is that when coordinates are converted to maps, the first coordinate is treated as the row index and the second one is the column index. So you either flip your head or do another transpose if you really want to compare with the expected result in the task description. Either way, to solve the problem, it's not necessary to transpose because the score calculation does not depend on it. However, if we check the shape, the test data ends up being a 10 times 7 grid after 100 iterations. This is because the unvar operation only creates the grid up to the largest coordinate value found in the data. To make sure that our grid is the same shape as expected, we take the field size and fill the missing values with 0. Now our last row is filled up too. It's also important that the unvar function will show numbers greater than 1 when coordinates overlap, so when several robots occupy the same position. This is also convenient for us when it comes to scoring. To calculate the final answer, we need to split the field in 4 rectangles. The field sizes are always odd, 11 times 7 in the test and 101 times 103 in the real data. And we must exclude the middle row and middle column. One way to solve this is using the stencil modifier. We are able to take chunks from an array with a specific size. The good news is that it works perfectly on 2D arrays as well. And I will highlight some features mentioned in the documentation which we definitely need. We can do non-overlapping chunks and we can also use the stride parameter. The example here showcases exactly what we want to do in the AOC task. With the sample data, the field size is 11 times 7. So we need 4 windows, each with a size of 5 times 3. And the stride needs to be larger by 1 in each direction, so that the middle row and column are skipped. Let's see how this works on the map. Okay, now to make this work also for the real field size, we can derive the size parameters of the stencil from f. First, we divide both values by 2. We get 5.5 and 3.5, which is halfway between both of the target parameters. So we can fork, floor, seal to create the window size and the stride at the same time. We combine them with couple, and now we can check if it works with stencil again. Now instead of identity, we can actually pass a function to stencil to do something with each group of values. To count the drones in each quadrant, we need to deshape and reduce add all the numbers. This will take care of any drones that occupy the same position. Finally, after another deshape, we can reduce multiply to calculate the safety factor. And all we have left is to combine all these functions to arrive at the solution of part 1. With part 2 unlocked, the big surprise is that there is a picture of a Christmas tree hidden in this challenge. We have to find out after how many iterations the robots will organize themselves in some shape which is really unspecified by the AOC text. So this leaves a lot of programmers puzzled. I will do my best to avoid showing any spoilers, but for this we will need to work with the real data because the sample is not going to arrange itself in a particular way. We can actually pull in the input file to the online editor and read it with the @fras function. We changed the field size parameter too, so let's check what we got so far. So here comes the mind-blowing feature of the Viva online pad, that it will convert anything that is shaped like an image to an actual image. We can just put the initial state here as a 2D map and we get a nice little black square with white dots. Technically, this is a grayscale bitmap, where 0 stands for black and 1 or any higher number stands for white. In a native environment, I mean if we run this on a locally installed Viva, we can convert it to an actual image with the img function and then write it to a file with @fwa. For now, we will just keep using the online pad. First, we can upscale the image a bit for better visibility. There is an easy idiom for it that also has an alias, cork. Keep on row keep, and a number to scale in both directions. 5 pixels will give a large enough image. So this is how the robots were positioned in the first place. We can change the number of iterations and observe how they all move. And even better, Uiua is able to generate an animation for us, combining all the snapshots in an animated GIF. For this, we just need to run the simulation for a range of numbers, and the additional array dimension will be the number of frames. At this point, we just see a lot of white noise. If we run this natively, we could have better control over the amount of time between each frame. We could also overlay the frame number on the image using the layout function. And some people may have actually tried this, browsing over many images until they find a Christmas tree. Especially when we have Viva and it's so easy to generate pictures, this approach is very tempting. As the saying goes, if you have a hammer, then everything looks like a nail. But you never know how many images you have to look at. The solution space is actually the multiplication of the two field size values, because they are co-primes. After that many iterations, the patterns will eventually repeat. Well, you can make some guesses, and AOC will tell you if the result is higher or lower. But in fact, there must be an algorithmic solution to this, which is not too difficult to guess. Our working assumption is that when the drones organize themselves in the shape of a tree, then their positions will have some special attributes. Maybe the image could be symmetrical, but we have no hint to support this theory. Maybe the drones are placed in unique positions, not overlapping, but there could also be other frames where this is true. Or the drones could converge to a specific part of the image. Now here's a spoiler. The clue was there all along, when the problem description gave us the formula for the safety factor. We can use this to our advantage. Let's examine a baby example of 12 drones. If they are completely dispersed and there are 3 drones in each quadrant, the score is 81. If they are a little more focused, with 6 drones in one quadrant and just 2 drones each in the rest, the score gets lower. If we go even more concentrated, the score gets even tinier. Even if we don't assume complete concentration, when the safety factor could theoretically reach 0, but finding the minimum safety factor might get us to the solution. So how to do it? We calculate the score for each iteration up to the multiple of the field size values, which is 10,403. Run the routine for each value. This can be done even in the online pad in reasonable time. Find the smallest value with reduced minimum, use the by modifier to keep the scores on the stack, and find the index of the minimum in the list of scores. This is our solution to part 2. And just for fun, to confirm our theory, we can draw the image of this specific frame now. Hence, the Christmas tree becomes visible. The Easter egg in this challenge was a really interesting and unique idea, and Viva had several awesome features coming to our aid. Pervasive functions that work on large arrays, a flexible stencil function to slice into multiple array dimensions, and even image generation capabilities have proven very useful in solving this problem. All things considered, this particular day was a perfect one for Viva. If you enjoyed this video, then don't forget to show your appreciation and see you in the next one.